So the next concept is the concept of instruction cycle. So what does an instruction cycle basically mean? Imagine we have a machine instruction. Let's look at this instruction, right? So we have already seen this, right? Load into accumulator whatever data that is there in memory location 2080. This is one of the simple instructions that we have seen, right? So we've already encountered, again, this is in 8085 syntax, right? So this is basically one instruction for an 8085 processor, right? So now given this, so what does this do? This loads whatever data is there in this memory address 2080 into the accumulator. That's what it does literally. So an instruction cycle is basically a sequence of things, that sequence of steps. You can think of it as a sequence of execution steps. You can think of it as a sequence of execution steps that are performed by the CPU so that it can execute one instruction. So let's say this is instruction 1. So given one instruction like this, what are the sequence of steps that are performed by the CPU to actually execute this? Okay, there are broadly speaking two parts to an instruction cycle. The first part is called the fetch cycle. The objective of the fetch cycle is to basically fetch this instruction itself. Remember, what we are looking at is a stored program model, right? So these instructions are actually stored in the memory itself. So the CPU has to fetch each of these instructions one after the other using the system bus from the main memory, right? So fetch cycle basically is all about fetching this instruction itself and everything that is needed. So this is basically fetching the instruction itself which we want to execute. Second comes the execute cycle. So the instruction cycle has two parts. First part is it fetches whatever instruction and whatever needs to be executed from the main memory. The execute cycle is all about executing whatever is the intent behind this instruction, right? So in this video, we'll focus a lot on the fetch cycle, right? Because the execution cycle itself is dependent on how the CPU is organized. So the again, we'll learn about multiple types of CPU organization in a little while in the future videos. So the execution cycle we will learn in lots of detail when we learn different ways of organizing a CPU. Because there are different types of CPUs. We'll learn about them and how they actually work. So these different types of CPU organizations have different types of executions of the instruction that is fetched from the memory, right? So what we'll learn about is a fetch cycle here. And to learn about fetch cycle, let's take a simple program so that it makes much more sense for us to understand how everything is flowing here, right? So it's very important for us to absorb this concept. That's why I'm taking a simple example here, right? Imagine I have a program. Imagine this program has 3 instructions. This is my instruction 1. This says load whatever is there in this data, in this memory location, whatever is there in the memory location 2080. So let's assume that this is in hexadecimal. Okay, so this 2080 is a hexadecimal number. So whatever data is here, load it into the accumulator register. That's my instruction 1. My instruction 2 is an instruction called SIM, S-I-M. Again, here I'm using an 8085 processor just to explain this concept. But similar, again, we'll also look at, after we understand the fetch cycle, we'll also solve a couple of problems where we'll see how other processors also will work. Right here, I'm taking an 8085 processor, which is an 8-bit processor. Let's not forget that, right? And 8085 processor has 16-bit addresses, right? It has 16-bit addresses. We've already studied this, right? 8086 has 20-bit addresses. 8085 has 16-bit addresses, right? We've already seen this. Okay, so let's assume I have 3 instructions like this, right? Load into accumulator 2. So let's assume my program only consists of 3 instructions. I hope with these 3 instructions, I can give you a good sense of how the fetch cycle itself works. So load into accumulator whatever data is there in 2080. That's what the first instruction wants us to do. The second instruction is called SIM. So the SIM instruction stands for, so this SIM basically stands for set interrupt mask. So SIM means set interrupt mask. Again, we learn about interrupt masking and how this command itself works when we learn about IO processing. Okay, one of the chapters in this course is called IO processing, where we learn about interrupt masks in lot of detail. Right now, just remember that it is an instruction. It is part of one of the instructions of an 8085 processor. Next, here is a third instruction. What does this? So MVI. So MVI stands for move immediate. So MVI basically means move immediate. Okay, so what does the move immediate? So MVI A. So 8085 actually has a bunch of registers. Okay, bunch of registers that the users can use. It has registers named A, B, C, D, E, H, L. These are the registers which the user can use in an 8085 processor. In addition to these registers, there is also other registers called program counters, accumulators, etc. So here move I A means, and 23H. This is an hexadecimal. Remember, whenever I say 23H, so whenever I say 23H, I mean hexadecimal. So I could also write this as H or base 16. So whenever I write base 16, it means hexadecimal, right? Or I could also write 0x23. This also means that this is hexadecimal. Okay, so hexadecimal, you will encounter hexadecimal being written like this, or with a H here, or with a base 16. Right? So what this means is, store this 23 into register A. Move immediately this value 23 into register A. That's what this instruction says. Right? Very simple. Again, this is very simple. This is basically copying a constant value into a register. That's what it's doing. Interrupt masks we'll understand as we progress through the course, especially when we learn about IO processing. Okay, now all this, so this program has, let's say, 3 instructions. I've taken these instructions, intentionally I have taken them. Okay, intentionally I have taken these instructions because I can show you multiple cases. Okay, so this program now is stored in your main memory. At the end of the day, this program has to be stored in your main memory. So let's assume this is my CPU, this is my 8085 microprocessor, and this is my memory. Look at my memory addresses. They start from 0000, go up to FFFF. Okay, again, these are in hexadecimal. The moment you see something like this, you should realize that this is hexadecimal. So each hexadecimal value corresponds to 4 bits. So this whole address is 4 into 4, 16-bit address. Perfectly works all right, because 8085 also has 16 address lines, right? Very simple concept, right? Now what is the, so again, let's assume my memory is such that one word equals to 1 byte. So let's assume this is 8 bits or 1 byte. Okay, my 8085 is also an 8-bit processor, which means any data that it reads, it will read via the system bus, it will read 8 bits at a time. Very simple concept here. Now let's assume this program, remember, this program before it gets executed, this program has to be loaded into the main memory. You see, this program has to be loaded into your main memory or RAM. If the program is not in your main memory, the CPU cannot execute it. So there is actually a software component called as loader. Again, we will learn about loaders in lots of detail in operating systems, right? A loader is a very important piece of software. See, whenever you compile a program, let's assume you have written your program in C language. You have written your C language program. The compiler, like GCC, a very popular C compiler, open source C compiler, it translates this C programming language into machine level language, right? So this machine level language code has, so the loader, so there are 2 pieces, loaders and linkers. Again, we'll study them in lots of detail in the operating systems course, right? This loader's job is to take the machine level code and load it into the main memory. That's why it's called a loader. Loader is a very important piece of software that is typically, again, sometimes loaders are part of the operating system. Sometimes there are special programs that exist. Okay. So this loader actually takes the machine level code and places it into the main memory. So imagine, look at this. So your LDA, so let's assume in this, so this whole program, let's assume is loaded into the main memory with the starting address. Let's assume my starting address where I have loaded this whole program is 0000. Now, if I see this whole program in the main memory, the way it looks is this. Look at this, your LDA. This LDA is called, this whole thing is one instruction, right? This whole thing is one instruction. This instruction has 2 parts. This is called as the op code or the operation code. This is called as the operand, right? So this is called as the operand. In this case, this whole thing is called the op code. This thing is called as the operand. There are cases where you can have multiple operands also. So the way it works is your LDA, remember your LDA also gets translated into binary at the end of the day because your microprocessor only understands binary. So your LDA, let's assume, takes 8 bits. In the case of 8085 microprocessors, each of these opcodes require at most 8 bits, and you can store all of these opcodes in 8 bits, right? So that's why they're stored in 8 bits. So what happens is, look at how my program is stored. Okay, which is my first instruction? My first instruction is LDA. So my first instruction opcode is LDA. So I store whatever is the binary code for LDA for the 8085 processor. I stored it in address 0000 byte, and this memory is byte addressable. Remember, this memory is byte addressable, which means I can address each byte and I can fetch the data of each byte. We'll look what happens if you have a 16-bit microprocessor, if this is word addressable. We'll solve some problems in this video itself little later. But first, let's understand the basic concepts. Okay, so see, look at this. This LDA, this opcode has a corresponding 8-bit internal code which is stored in this first byte. Then in the second byte and third byte, look at this. This is 2080 base 16, which means it requires 2 bytes. This requires 1 nibble or 4 bits. This requires 4 bits. This requires 4 bits. This requires 4 bits. Very simple concept here. So this is stored here. Look at this, 2080. This is how it is stored. Right? Very simple concept here. Again, here we are using the little endian system, because by default everything is a little endian system unless stated otherwise. We'll use little endian as the default way of storing these numbers. Okay, so this requires 2 bytes. So literally your whole instruction 1 required 3 bytes. In the first byte I'm storing LDA. The second byte I'm storing 80. In the third byte I'm storing 20. Okay, cool. My second instruction, this has only an opcode. It doesn't have an operand. So I can store it in 1 byte. So my second instruction is stored here. So my first instruction is stored in these 3 locations. My second instruction is stored in just 1 byte. My third instruction, look at this, MVI A, right? So because this has a fixed number of registers, MVI A is basically 1 opcode. Similarly, in 8085, we'll also encounter MVI B, MVI C. Each of them has a unique binary value. So here my opcode is MVI A. So MVI A is stored in 1 byte. Look at this. And this constant 23, this is in hexadecimal, right? So this requires 4 bits, 4 bits. So total of 8 bits or 1 byte. So this whole program required 5 bytes. Look at this. It required 5 bytes to be stored. This is how it's stored now. Okay. So this is how it's stored in the main memory. Now, how is this whole thing fetched from the main memory? See, first we have understood how it is stored in the main memory itself. Now, how is it fetched? So there is a very important register within a CPU. Most modern CPUs have it. This is called as a program counter. So what the loader does is, when the loader says, I want to see, the loader loads the program onto your main memory with a, let's assume this loader loaded this whole program starting at address 0000. Then what the loader does is, as it starts executing this whole program, it also places this first address. It is the address of the first instruction that needs to be executed. It stores 0000 in the program counter. Remember, if this is my 8085 microprocessor and all these are my registers, I have 2 very important special purpose registers called program counter and accumulator. Most modern microprocessors have a program counter. So what the loader, just before executing, what it does is the program counter's value becomes 0000, indicating that the next instruction that has to be executed. Program counter always stores the address of the next instruction that has to be executed. Right? Very simple concept. So since the loader wants us to execute this program, the program counter's value is 0000. Now what the microprocessor does, now this is very important and interesting. What the microprocessor does now is it reads this value which is there in the program counter. It reads that the value is 0000. Now the CPU, the microprocessor itself, now uses a system bus and says, fetch whatever data is there in 0000. It fetches this. Then it sees, look at this, whatever data is there in 0000, because that's the, and it knows that my opcodes, because my microprocessor is an 8-bit microprocessor and because my opcodes are only 8-bit, it first fetches the first byte, and this memory is also byte addressable, making our life simple, right? It fetches this whole thing. Okay, the microprocessor now sees LDA. The microprocessor fetched this data by querying the address at PC. It saw that it is an LDA. It saw that the opcode is LDA. The moment it sees an opcode of LDA, it knows that LDA is a 3-byte instruction. Look at this. It knows that LDA is a 3-byte instruction because LDA itself requires 1 byte. Then we'll give a memory address. That memory address itself is 16-bit. It knows that this is 16-bit because my 8085 microprocessor addresses are 16-bit addresses. Right? So it knows. So the microprocessor already is aware of the fact that whenever you have LDA, we have to fetch 3 bytes. So what, again, that is already known to the microprocessor. The designers of the microprocessor have already designed that logic circuit within the microprocessor itself. So it actually sees that LDA requires 3 bytes. It has already gotten the first byte. So it will go and say, okay, get me the next byte and get me the next byte. Right? Because it knows that LDA is a 3-byte instruction. Look at this. LDA instruction in 8085 is a 3-byte instruction. So what it does is it says, now let me fetch it. So then it will fetch the whole thing. It will fetch LDA 2080. It fetched the whole. It fetched the second byte and the third byte. Now once it fetches this, before it starts executing, look at this. See, look at this. It fetched this. Now it will start executing. So my fetch cycle is over now. My fetch cycle is over. Now it will go into the execute cycle. Right? Wherein it will start executing the whole, this instruction it will start executing. While executing this instruction, the program counter gets updated. And the program, because the program counter is already executing. Look at this. This instruction that was stored at address 0000 is already being executed. It went from fetch cycle to execution cycle. Right? Because it's now in the execute cycle, this program counter has to point to the next instruction. And so what it does is the program counter gets updated. So what happens is the program counter becomes program counter plus some step size. And because we know that the LDA instruction requires 3 bytes, the step size here is 3 bytes. So what happens to the program counter now? 0000 plus 3. Right? My step size is 3. So what happens now? My program counter, while my program counter becomes 0003. And when does it become? Look at this. While the microprocessor is executing this LDA instruction, my program counter starts pointing to the next instruction already. So my program counter is now, see, initially my program counter was pointing to this. While this whole instruction is being executed now, my program counter updates because it knows that LDA requires 3 bytes. It knows the next instruction will lie at address 0003. Now, as soon as this instruction is executed, completed, see, let's assume this is completed now. After it is completed, my program counter will say, okay, so my microprocessor goes back to the program counter and says, because microprocessor knows that the address of the next instruction is already in the program counter. Right? So the microprocessor now says, get me whatever data is stored at address 0003 or 0003. Okay, then it fetches this. Now let's see what happens, right? Now it fetches this. Now it fetches whatever data is at 0003. So it gets SIM. It knows, this microprocessor knows that SIM requires only 1 byte. So the step size becomes only 1 byte. Look at this. The step size becomes only 1 byte now. Right? So while the SIM instruction, we don't require to fetch anything else because SIM is a, look at this. This is a 3-byte instruction. This is a 1-byte instruction. This is a 2-byte instruction. The microprocessor already knows this. So the moment it fetches SIM, it knows that I don't have to fetch any more bytes. My step size becomes 1. And while SIM is being executed, my program counter will become 0004. So now my program counter points to this. It no more points to this. While my program counter is updated based on the step size, which itself is dependent on the instruction that is currently loaded and that is currently being executed. Right? Your program counter already updates while this goes into the execution cycle. Right? Very cool. So this instruction is also executed. Next, the microprocessor asks the program counter, okay, what is the next instruction? And that's very clear. The next instruction is at 0004. Then it fetches this 8 bits. It realizes that it is MVI A. Now this microprocessor knows that this is a 2-byte instruction. So because it knows that this is a 2-byte instruction, it goes and says, so it makes the step size equals to 2. It goes and fetches this 23 data also. So it fetches this 23 in hexadecimal and the step size becomes 2. The step size is dependent on the opcode because by just looking at the opcode, we can say whether it's a 2-byte instruction, 1-byte instruction or 3-byte instruction. Now, while this is being executed, my program counter gets updated. My program counter gets updated pointing to 0006. Right? Suppose if I have more instructions, it will keep executing. Very importantly, please remember that the program counter always points to the next instruction that has to be fetched. That's very, very important. Very, very important piece of logic here that we cannot mess up. Okay. So I hope this whole logic is clear. It's a very simple concept. It's not rocket science. It's a very, very simple concept here, right? Now, there are two types of CPUs as far as instruction length is concerned. Look at this. This is a 3-byte instruction. This is a 1-byte instruction. This is a 2-byte instruction. There are some older CPUs which have fixed length instruction CPUs. They're called fixed length instruction CPUs, where all instructions are of same size, are of fixed size or fixed length. Okay, these are not popular anymore. Today, even slightly older microprocessors like 8085, 8086, all the modern processors have variable length instruction CPUs, which is exactly like this. Every instruction has a different length. So if you have a fixed length instruction CPU, right, then your step size is fixed, right? You don't have to keep updating the step size. The step size is also fixed. Here the step size, in this case, as we have seen just now for 8085 processor, your step size is dependent on, your step size is a function of the opcode that you have fetched from the memory, right? In this case, in the fixed length, again, very old CPUs used to have the fixed length instruction CPUs. They are no more popular today. But it's important to understand the evolution of CPUs themselves. Again, it's very important to learn what are some of the older technology also. We'll point you to lot. Again, even 8085 is not state of the art. It's a fairly old technology, but it's a simple enough microprocessor for us to understand this subject. As I told you, if I jump and explain you i7 or i5 processor, I mean, it will take many hours of explanation and you will panic just looking at the pin diagram. Here the pin diagrams are very, very simple for 8085. Even 8086 can get slightly more complicated. So it's very easy to understand concepts from the perspective of the simplest of microprocessors. Okay, because the concepts stay the same. Whether you have an i7 processor or i9 processors were launched recently, tomorrow if i10 processors are launched, or new ARM processor like new ARM processors which are used in iPhones and iPads come up, it's okay. The core concepts stay the same, right? If you ever become an IoT engineer, most likely you will not use an 8085 or 8086, but the concept you learn here will stay with you, right? So that's why it's very important to learn some of the older concepts also, like these fixed length instruction CPUs, which are not popular anymore, right? So now let's look at simple problem. Okay, let's look at a very simple problem here. So let's assume I have a 32-bit microprocessor. Look at this. I have a 32-bit microprocessor, and let's assume I have instruction 1 which requires 2 words. Now if I have a 32-bit microprocessor, what does one word here represent? One word here represents 4 bytes, right? One word here represents 4 bytes in this case, because when in a 32-bit microprocessor, what happens? When I fetch data from the main memory, I can fetch 32 bits in a single shot. 32 bits equals to 4 bytes. So let's assume I have a program where instruction 1 is 2 words, instruction 2 is 1 word, instruction 3 is 1 word, so on and so forth. I have a bunch of instructions. I have 7 instructions here. Now let's assume this whole program is loaded into the main memory and the starting address is hexadecimal 234. 0x basically means hexadecimal. The starting address is 234. Okay, this is the address. Okay, and the memory here is byte addressable. This is very important. The memory is not word addressable. The memory is byte addressable, which means I can exactly fetch 1 byte if I want. Now the question here, the core of the question here is, what is the value of program counter when i6 is being executed? Now let's see that. Okay, when i6 is being executed. Now this instruction started from 234 hexadecimal. Okay, here I'm assuming that all these addresses are in hexadecimal and it requires 2 words. What does 2 words here mean? 2 words mean 8 bytes because 1 word is 4 bytes. So 234 plus 8. 234 plus 8. So 8 plus 4 is 12, right? So in your hexadecimal, you have numbers from 0 to 9. Then you have A, B, C, D, E, F, right? This is 9, 10, 11, 12. So this becomes 23C. So we are doing hexadecimal addition here, right? So 23C. So which means my next instruction will start from 23C, right? So 234 to 23B from here to here is your first instructions location, right? Very simple. Again, here please don't forget that this whole memory is byte addressable. which means I can actually address 1 byte if I want, right? And the starting memory location is 234 and 1 word is 4 bytes because we are using a 32-bit microprocessor. Very, very important to grasp that, right? So now again, if you know how to do the simple hexadecimal addition, this is simple. This requires 1 word, right? So this requires 1 word. So 23C plus 1 word. 1 word is 4 bytes. So let's do 4 bytes addition here. So C plus 4 is 0. 16. So C is 12. 12 plus 4 is 16. 16 is 0. Right? 1 gets carried away. This becomes 240. So this instruction will get stored from address 240. This requires 2 words. 2 words means 8 bytes. Right? 2 words is 8 bytes, right? Very simple. So this, so this is the starting address of this. Sorry, now I need to compute this. I'm sorry. So 240 is the starting address of this. So this plus 1 word. 1 word is 4 bytes. So the starting address. So I'm only writing starting addresses here. Okay, I'm only writing starting addresses of each instruction. Ending addresses, you can compute this. This minus 1 is this. This minus 1 is the ending address of this. So let me just write the starting addresses so that it's less confusing. So 240 plus 4 bytes. So this becomes 244 bytes. The starting address of this instruction is 244 bytes. 244 plus 8. 244 plus 8 is 24C. Right? Because 4 plus 8 is 12. 12 is C. That's why we have C. Then I have 1 word. 1 word basically means 4 bytes. So this will become 250. Right? 250 plus 2 words. 2 words is 8 bytes. So this will start from 258. Right? So the next, so this will require, if I have instruction 8, so till where will this be? So this is 1 word or 4 bytes. So this will go to 25C. Right? So if I have other instructions. Now what is the question? Let's go back to the question. The question asks us, what is the value of program counter when I6 is being executed? Look at this. When I6 is being executed, the program counter will point to the starting address of I7. That's what it will point to. Right? What is the starting address of I7? I7 starts from 258. So the answer here is 258 in hexadecimal. 258 in hexadecimal. I'm sorry. That's it. Very simple. Here, this problem, you have to be careful that the memory is byte addressable. And what we have is a 32-bit microprocessor, which means 1 word is 4 bytes. And then everything will fall in place. Again, this is obviously a variable length instruction CPU because each instruction has different number of words or different size. Each instruction is of different size. That's why it's a variable length instruction CPU. We don't have to be told that explicitly, right? Because each instruction is of different length. We already know that. Very simple concept, right? Okay, let's look at one more. Okay, let's continue on the same example like before, right? Same example as before. So same as above, everything stays as same as above, except that the memory is now word addressable. Look at this, my memory is not byte addressable. My memory is now word addressable. This is very interesting. And 1 word is 32 bits, which is 4 bytes. Okay, let's assume the program starting address is 2346, right? So instruction 1, this is decimal. Here we are given decimal numbers. So 2346 is the starting address. So 2346 is the starting address of my program, which means my instruction 1, which requires 2 words, is going to start from 2346 in decimal. So we can just do decimal counting. So instruction 1, remember, instruction 1 requires 2 words. And this memory is word addressable. So I'll only add 2 here because the memory is not byte addressable. When it is byte addressable, I convert the words into bytes and add the words. Add the bytes. Right here, since the memory itself is word addressable, I just need 2 words now. Because it says I1 requires 2 words. So which means what happens now? So 2 words is, so the address of instruction 2 will start from 2348 because I1 requires 2 words. Similarly, now let's go to I3. So how many does I2 require? I2 requires 1 word. So I'll just add this 2349. And again, this is decimal. Remember, these all are in decimal. I'm only doing the decimal part. Similarly, so the question here is, what is the program counter value in decimal when I6 is being executed? Same, very simple question. The only difference between the first and the second question, the only difference between this and this is, here memory is word addressable, here memory is byte addressable, which means every address points to 1 byte here. Here every address points to 4 bytes or 1 word. That's the core difference here, right? So now I3 starting address, we already got it to be 2349. What is I4? So I3 requires 1 byte. sorry, one word, I'm sorry, one word. So just add one word to this. So I get 2350. How much does I4 require? I4 requires 2 words, right? So this will be 2352 starting address. I5 requires 1 word, which means I6 starts at this. I6 requires 2 words, which means I7 will start from 2355 and it will go up. It requires 1 word, right? So 2355 up to 2366, right? So what is the question? What is the PC value, program counter value, when I6 is being executed? When I6 is being executed, program counter points to I7. So the answer here is 2355 in base 10. That is important, right? Again, here I wanted to show you the difference between word addressability and byte addressability. In byte addressability, every address points to 1 byte. In word addressability, every address points to 1 word. Here in this case, 1 word is 4 bytes. Okay, that's the important distinction that I wanted to bring to your notice. Okay, now let's look at one more question here. Imagine I have a CPU which is a 24-bit instruction programs. Okay, so here it says I have a CPU with 24-bit instructions program, which means this is a fixed length CPU, fixed length instruction CPU. So this is a fixed length instruction CPU, because all instructions, because it says my CPU instructions are all 24-bit or 3 bytes, right? So all my instructions are 3 bytes. So this is an old school microprocessor. It's an old microprocessor. The program's load address is 300 base 10. So the program loads at address 300. Okay, this is where it loads. Which of these is a valid value of PC? Very simple question. Look at this. Again, here we are assuming that, again, default assumption is my memory is byte addressable. My default assumption is that my memory is byte addressable unless stated otherwise. So at address 3000, I can store 1 byte. Okay, at address 301, again, these all are in decimal. Remember, all these are in decimal. I can store 1 more byte. 302, I can store 1 more byte. Right, this is my main memory. So now, since I know that each instruction is 24-bit, each instruction requires 3 bytes. Each instruction requires 3 bytes. When this instruction, which is loaded at 300, is being executed, my PC value will be 303. This is one instruction. From 303 to 305 will be my second instruction. From 306 to 308 is my third instruction. So on and so forth. So what are the values that your PC will point to? PC or program counter will initially point to 300. Because all instructions are 3 byte instructions, my PC, as soon as this is being executed, it will point to 303, then it will point to 306, it will point to 309, and so on and so forth. So all the addresses that it points to can be written as 300 into some I into 3. Right? It has to follow this, right? Because each instruction, this is my first instruction starting address, my second instruction starting address, my third instruction, my fourth instruction, so on and so forth. So all these program counter values have to be 300 plus some multiple of 3. Now which of these is a valid value? Look at this. What is the difference between 300 and 400? Only 100. 100 is not divisible by 3, so program counter will never point to this. The difference between 300 and 500 is 200, not divisible by 3. The difference between 300 and 600 is 300. So 300 plus 100 into 3. So this is a valid value of program counter in this computer. So this is also not a valid value. So option C is the right option here. Very simple question, slightly twisted, but a very simple question if you understand about the fixed length instruction CPUs, right? So now let's get a high level overview of the execution cycle itself. The execution cycle, see, look at this. I'm loading the opcode and the operand, right? We have seen what an opcode is, what an operand is. The actual execution depends on what the opcode is and what are the values in the operand, right? So this is called as so again, we have seen multiple instruction formats, right? We have seen 1 byte instruction, we have seen 2 byte instructions, we have seen 3 byte instructions, so on and so forth, right? There are multiple CPU organizations that we'll start learning from the next video. And we'll learn about execution cycle of each of these types of instructions when we learn CPU organizations. Because based on the CPU organization itself, the execution cycle will differ. Right? So in execution cycle, what do we have already loaded this. We've already gotten what is the opcode, what is the operand, or what are the operands if there are multiple operands. Now we have to execute it. The way each of these instructions get executed in the execution cycle depends a lot on how the CPU is organized logically, right? So we'll learn about multiple CPU organizations, and as we learn each CPU organization, we'll also learn how the execution cycle and what types of instruction formats, like 1-byte instructions, 2-byte instructions, 3-byte instructions, what types of instructions does each CPU organization each CPU organization can facilitate, right? So we'll go into the depths of execution cycle in the context of CPU organizations and in the context of instruction formats which a CPU organization can handle, right? So we'll see that. We'll see over the next few videos, we'll see that, so that your concept becomes much more clearer.